Hello and welcome to your first lesson video in physics. So in our first unit, measurement and uncertainties, we're going to be starting with section 1.1. Now we're not going to be covering 1.1 in its entirety, but we're going to be doing most of it. Now something I want to just point out is that if you haven't done so already, pause the video and print out a copy of your formula booklet. If you don't have a printer, go ahead and just write out the formulas as you see in the formula booklet. So you have a hard copy. It's really important to have a hard copy, okay? So it looks something like this, right? You've got your fundamental constants, your metric multipliers, unit conversions, symbols. Now, okay, when you turn the first page, the first thing you're going to see is the fundamental constants. So we're going to be referring back to this page quite a bit throughout the course. Next page, we've got the metric multipliers, which we're going to cover in this lesson, but now you know where to find it in your data booklet. What else? Unit conversions. This stuff, I mean, we'll get to it when we get to it, so I'm not going to go into that too much right now. Electrical circuit symbols. Again, we'll get into that when we study electricity. And the main units, main equations start right here. Equations core. And notice that every single box is labeled with the number. So for example, 1.2, 1.3, 2.1, 2.2, 2.3, 2.4. Okay, so and these formulas just continue on the next page and on the next page. Now, we're not going to be doing some of these formulas this year. This booklet covers the formulas that we're going to be learning not only this year in grade 11 physics, but also if you decide to take grade 12 physics. It's all in here. And in fact, there are some formulas in this book that you're not even going to use at all throughout both courses, because either it's part of IB physics or it's part of the higher level IB physics, which we don't even cover at the school. So that's why you might not use all the formulas in this booklet. Now, speaking of the IB, I do want to mention something in case some of you are wondering why the textbook says physics for the IB diploma. So physics, at the end of the day, is physics. It's made of forces, there's matter, there's energy, and there's conversions in between. It doesn't matter what audience it's being targeted towards. It contains the same information. Now, the way in which that information is presented differs, and this book does an absolutely stellar job of communicating these ideas and giving examples, and has a really nice problem set. So that's why we're using this book. Not to mention that this book covers everything you're going to need to know for both grade 11 and 12 physics. So when we start going through the sections, after all, for example, in chapter 1, we're only going to be covering part of 1.1, and we're going to be covering, actually all of 1.3, but none of 1.2. Right? So 1.2 is something that would be covered in IB. So if we don't cover something in the contents, that means it's either covered in IB. For example, all of these are, let me show you, sorry. All of these are IB, so we're definitely not covering any of those. And sometimes in between these sections, there are either grade 12 topics or they're just IB. So we're not going to cover them. Okay, so in case you're wondering why certain things get skipped, that's why. Okay, so the first section begins on page 1, and you're going to know the page because it's on the bottom right of your sheet. So this is 1.1, measurement in physics. So everything in this book, it supplements what we do in the lesson videos. So when you're done reading the lesson videos, or even before, whichever one you'd like, read through the book, go through the examples. And I really like this book for its worked examples. They have really nice ones. Okay, so there's the example, there's a solution, okay? And then eventually when you get to the end of your section, as you would expect in any book, there's your practice problems. And in this book, the practice problems are in a sort of yellow box. Okay, so there are 22 practice problems here. You don't need to necessarily do all of them. You'll know which ones you have to do based on what's assigned. But I just wanted to show you that. Okay, so I apologize for the sniffling. So I've got some allergies right now. So, well, they're acting up at the moment. But here we go. All right, so we're going to go ahead and dive into section 1.1. So we're going to go back to the slides. Okay, so what I would recommend also, if you have a printer at home, I would really strongly encourage you to print out the slides, the student version of the slides that I post on Teams before you start the lesson. And if you haven't, you can pause it and go print it right now. Usually what I like to do is print 3 slides per page, or I can print 6 slides per page, or even 4. You can do 2. Depending on how much paper you're willing to spend. So there's that. So you can fill in the slides as we go through them in class. If you would rather take notes by hand, that's good. But some form of writing you need to be doing alongside watching these videos, okay? Reading something on a screen is not nearly as impactful as writing it yourself. When you write things down, you're putting it into your long-term memory. So I strongly encourage you all to do that. Okay, so let's get started. When most people think of physics, the first physicist that jumps into most people's minds is Albert Einstein. And if it's not Albert Einstein, it's probably going to be the next guy that I'm going to put on the screen. Okay. Albert Einstein and his famous equation, E = mc squared, which we're going to learn about a bit this year, and we're going to learn a bit more in grade 12 physics. Okay. If you didn't think of Albert Einstein, you might have been thinking of Sir Isaac Newton. Now, Sir Isaac Newton didn't just contribute a lot to physics, he actually contributed quite a bit to the field of calculus as well. A really nice subject to study. I mean, if you're taking physics, it's kind of a no-brainer that you would be taking calculus as well next year. Okay, so they really do go hand in hand. All right. Now, Isaac Newton, you're probably familiar with the famous story of him sitting under a tree and having an apple fall on his head. And through that, he started to explore and analyze the effects of gravity. Okay. All right. Throughout grade 11 and grade 12 physics, we're going to be looking at these four physicists predominantly. Many others as well, but predominantly these ones. Galileo for his introduction of something called kinematics, and that's really what we're going to be studying in our first unit. Newton, like I said, he did a lot in calculus and also a little bit in dynamics. Dynamics is generally the first unit we do in grade 12 physics, but it has a lot of similarities to what we do in grade 11 physics at the start. Maxwell, he had a lot of equations related to light, and so therefore something called electrodynamics. You're going to notice something else actually that just popped up under Newton, classical physics. Right now that's not going to mean much to you, but classical means the original physics, and that's really what we're learning. We don't get to something called modern physics until we learn about Einstein at the end of grade 12. That's when the things start to get a little bit confusing and complicated. Right, so classical physics, this is the physics that can explain things that move at ordinary speeds that we're used to dealing with and regular sizes that we're used to dealing with. Modern physics is more for things that travel super fast and that are super small, hence relativity and quantum physics, respectively. Okay. Now, what is physics? Physics is the study of energy, it's the study of matter, and it's the study of forces. Okay, so, of course, there can be so much more that can explain and describe what physics is, but in reality, it comes down to those three main things. Now, no matter what you do in this world, no matter what you observe, there are always forces being exerted on objects by other objects. Okay, so look at the bighorn sheep. And these sheep like to fight a lot by putting their heads together. Now, when they put their heads together, there is definitely some kind of force of impact going between them. Right? But there is so many more forces that are occurring here than just the force of these two sheep headbutting themselves together. Now, there is definitely a force that sheep 2, let's call the sheep on the right on the bottom of the hill 2, and the sheep on the top left 1. There's definitely a force that each of them exerts on the other. But there are so many other forces acting in this system. So think about that for a moment. Pause the video and just take a couple seconds to think about what other forces are keeping those animals in place or are being applied on those animals at that moment in time. All right, hopefully you had a chance to pause the video and think about this. All right, so think about the following. When you stand on a scale in your bathroom, in your bedroom, or at the gym, a lot of people will say that they're measuring their weight. But in fact, the scales that you stand on to see how if you've lost weight or if you've gained weight or if you're at the same weight, those don't tell you your weight, although this is usually the terminology that's used in regular conversation. A scale does not actually measure your weight. A scale measures something called your normal force. And we're going to learn a lot more about that when we study elevators and the movement of elevators. But a scale doesn't measure your weight. It might sometimes measure your weight, but more often than not, it measures something else called the normal force. Think about this. When you stand on a scale, there are springs in this scale that have to push back up on you. And the more you weigh, okay, I'm using the word weigh, but the more massive you are, the more that your body is going to push down on that scale. And the more that scale is going to have to push back up on you to balance itself. And so the more force that those springs have to exert inside the scale back up on you, well, the more force it's going to read. Okay, so it's actually the upward force that the scale is measuring, and that's the normal force. It's a reactive force. Now, these sheep are standing on the ground. The sheep's, now I'm going to say weight here, but just go with me for a second here. The sheep's weight is moving itself down on the ground, and the ground is pushing back up on the sheep. That ground pushing back up on the sheep is called the normal force. Okay, I'm going to write all these down in a moment so you can start to take notes, and we're going to go into all of these forces in a lot more detail in later lessons. But for now, I just wanted to introduce them. Now, I said weight. Weight, by definition, since it's not what the scale reads, what is it? It's the force of gravity. That's what you need to remember. Weight is force of gravity. Okay, so every object that has mass, if you are made of even one proton or one electron, you have mass and you have a force of gravity. Now, whether it's us as humans, or maybe if you have a tennis ball in your garage, or whether it's these sheep on this mountain, they have mass. They're made of particles, and so they are going to be attracted to the Earth, which also has mass. Now, they get attracted towards the Earth, so whichever direction the Earth happens to be, and we always draw that direction as directly down towards the center of the Earth. In this case, we draw weight as going down. So we would represent that with an arrow going down, kind of like this. Now, in this animation, you've got all the forces coming up at the same time, so just go with me for a second here. So remember we said this sheep on the left was going to be number 1 and the bottom one number 2. So we're going to focus on number 1. Okay, so here's the weight force. Notice that the arrow is going straight down towards the center of the Earth, and we label it an appropriate symbol, W. Okay, W stands for weight. Again, weight means force of gravity. And then we even further specialize it by putting the subscript. We put the subscript 1 to imply that this is relative to object 1. Now, why is this arrow coming out of the center of the object and the other arrows are coming out of all different regions? Okay. Since weight has to do with particles, it has to do with matter and mass, you always draw the weight force coming out of the region where the center of mass of the object is. Now, for a sphere, imagine a sphere, a perfect sphere. Let me just go back to go to the page here and show you for a second. Imagine you have a sphere. Now, a sphere is a perfect geometrical object. Okay, building a perfect geometrical object in real life, it's probably not going to happen, but theoretically in mathematics, a lot of stuff can be done. Okay, the center of mass, so the location at which all the mass around this point is uniformly distributed, is in the middle. Okay, so that's the CM, or the center of mass. We're not going to go into center of mass in great detail. Okay, calculations involving center of mass, that's covered in a different subject called AP Physics. You may have heard of it. Okay, we're just going to slightly talk about the concept here and lightly introduce it. So this is the point in the object where the mass around it is uniformly distributed. And so for a sphere, that would be exactly in the center because it's a perfectly symmetrical object. Now, if you go back to the slide, when you have a sheep or an animal or a person, or really any other object other than a mathematically theoretical perfect sphere, the mass is not equally distributed. So what we do is we just make an approximation, right? And again, this is because we're not studying the AP Physics. We're just going to say that the middle of the object, so in this case, the approximate middle, where the gut is, that's where the weight is being exerted. That's where the mass is more or less uniformly distributed around. Okay, so the arrow comes out of the gut and it goes down, points down towards the center of the Earth. That's weight, force of gravity. All right, this N here, that's the normal force that I kept talking about. So imagine this for a second. If you tap the wall with your hand, I mean, you're going to feel something on your finger. If you hit the wall really hard, I mean, your hand's going to hurt afterwards. And if you punch the wall, chances are your knuckles are going to start bleeding. Why? You applied a very massive force on the wall, and therefore the wall reacts and applies a force back on you. Now, while you don't actually see the wall crunching itself into a fish shape and going at your hand, it's not working like that. The wall maintains its shape unless you destroy its structure. But when you apply a force onto an object, it applies an equal magnitude, opposite directed force back at you. We're going to study this in a lot more detail later on, again. So in this case, if you hit the wall really hard, it hits you back very hard, and that's what damages your hand. Most likely, you've also inflicted damage on the wall also. Okay, so that reaction force is called normal force. Notice that it's coming out of the ground. And where is it coming out of? It's coming out of right where their feet are. Okay, so why is that? So the object's weight, its mass, pulls itself toward the ground. So the ground would feel a force on it. Imagine someone was sitting on you. You would feel their weight on top of you, right? Their force of gravity. And so your body has to push back up on them to keep them where they are. If your person sat on a piece of tissue paper, it would break because the structure of the tissue paper wouldn't be able to support their weight. Okay, so there wouldn't be enough normal force supplied. In this case, the ground is pushing back up on the animal, and where? Right where their hooves are, or their feet. Okay, so the normal force pushes back up on the animal to keep it upright. Now, the normal force is always going to be perpendicular to the surface. This surface is on an angle. A lot of times, especially in grade 11, we don't necessarily deal with angled surfaces, especially not in the beginning. This is just right now a theoretical analysis, so that's why it's on an angle. But generally speaking, the normal force ends up being opposite in direction to the weight. But since we're on an angle here, just always remember normal force is perpendicular to the surface. All right, so we've got that. All right, now let's look at this little F force. This is the frictional force. Now, when you hear friction, you're probably thinking of some kind of resistance, right? A resistive force. Friction, by definition, is the resistance force between two solid objects that try to move against one another. All right. Now, because this sheep on the left is getting pushed back, well, there's a friction force acting on it, right? It's trying to hold itself in place. So there has to be some kind of friction as it's moving, right? So we've got a friction on sheep 1, we've got friction on sheep 2, and of course the respective weight and normal forces. And you can probably guess what these two forces are, F21 and F12. These are the forces of each sheep acting and pushing on the other sheep. Now, usually when we deal with force diagrams, and we'll have a better name for that later as well, we deal with just one object and the forces acting on that one object. All right, I think we talked a lot about this picture. Again, you can analyze it later if you'd like. We're going to analyze each and every one of these forces in so much more detail with mathematics, with calculations, not necessarily of this picture, of this scenario, but of other scenarios in later lessons. Okay, let's keep going. In chemistry, there's an experiment that can be done called the popping can. Okay, so it starts with a can being injected with gas. Okay, so you have a lot of pressure building up in this can. Now, if you have a valve, that pressure can escape. But if you decide to close off that valve, the pressure can build inside. Now, if the pressure builds inside enough, well, you can just blow the top of the can of pop right off. Actually, we do this in grade 12 calculus. We study why the shape of the soda can is the way it is, why it's not a perfect sphere, why it's curved around the edges. It all has to do with weak points and maximizing surface area. All right, so right now you have a lot of pressure inside of this can. Why did the top fly off? You have a lot of pressure inside this can, pressure pushing outside on the walls of the can, pressure pushing on the bottom, pressure pushing on the top. Now, the walls of the can, they're all shaped in a circular pattern, so this force is distributed rather equally. On the bottom, the force is going toward where the pop is sitting, which is a table or some kind of surface. That bottom base of the can is not going anywhere. But the top, there's nothing to hold it in place, so that pressure is going to blow it right off. Now, all of this pressure, this force, okay, specifically the force is measured in something called pounds. Now, in physics, when we're studying, we're not going to use pounds to measure force. Countries like England, they like to use pounds to measure force. We don't like to use it. In fact, you probably know that if you've ever traveled to the States, you know that they use different measuring units as well. For length, they use inches, feet, miles. We use centimeters, meters, kilometers. I am a huge proponent of the metric system, as is many countries in the world. There's actually, as I know, only 2 countries that don't use the metric system, and they are the United States, and there's a very small country somewhere in Eurasia, Africa region, they don't use it either. But the metric system is much better. If you're interested, I can do another video on that, but it's just makes sense. Instead of having different systems of going between different units, you just multiply by 10 or divide by 10 to go between each and every single type of unit in the metric system. It's so much more convenient and it makes sense. Anyways, for us, we're not going to be using pounds to measure force. We're going to use a unit of measure called the Newton. For any quantity that we measure in physics, we're going to have a specific type of unit that we're going to use to measure. Okay? So for example, force, like I said, will be measured in something called Newton. We'll learn all about these units in a couple of slides. Now, what's really interesting about physics is the science that you can explain everything in. Okay? Biology is the science of living organisms, life, right, and energy. Now, biology, when you really break it down, you have chemicals, molecules interacting with each other in certain ways. That's chemistry. And when you break down the molecules, you have atoms, and those particles interact via charges with their mass, via different forces. That's physics. At the end of the day, everything can be explained with physics, whether it's things of very small scales or things of very, very large scales. In physics, we have very large forces that we study. Things like hydrogen bombs, atomic bombs, nuclear reactions. Okay, we're going to study nuclear reactions this year and next year. It's really interesting stuff. Okay? How do you get an impact crater? You've got either an asteroid or a meteoroid, some large rock in space, a really large celestial object that barrels its way towards Earth, hits the ground, and based on that we can determine the speed, potentially its trajectory, where this object came from. Okay, so this is a crater in the Arizona desert. Luckily, it hit in Arizona, not somewhere where there's a lot of civilization. Okay. So physics is a study of the very large and the very small. Now, this is a picture of something called a barred spiral galaxy. The reason why it's called a barred spiral, well, the spiral you can see from the shape, and the barred, that's due to the elongated shape of the center, the nucleus, okay, as it's called, of the galaxy. Now, for us, we reside in something called the Milky Way galaxy, which is also a spiral galaxy, but it's not barred. Okay, so it doesn't have this elongated shape in the middle. It's actually more circular. Okay. Now in physics, there are two types of units, fundamental and derived. There are seven fundamental units, and they are in something called the SI system. We're going to learn later what that prefix means, or that abbreviation rather. It stands for Système International, so we'll come back to that. But there are 7 fundamental units. If we were in the classroom, you would see them hung up on the wall behind you. So a good idea might be to just write these down on a piece of paper and stick them to your wall so you keep looking at them. Okay, so the 7 fundamental units are mass, they're measured in kilograms, length, it's meters, time is seconds, temperature is measured in Kelvin, electric current, amperes, luminosity, candela, that's IB, mole is measured in mole. Okay, we're not really going to get into mole that much, but if you study chemistry, you're going to be seeing it a lot. Okay, so those are the 7 fundamental units. Now, in physics, there are way more quantities than just measuring temperature, length, mass, current, luminosities, and moles. We measure forces, we measure momentum, we measure energies. Right? There's a lot of stuff that gets done. And so that means we need more units, but these are the 7 fundamental ones. That means that the derived units, right, so other quantities other than these, okay, they have units that come from these 7 fundamental units, right? So they can be derived from these units. All right. Now, randomly throughout these videos, you're going to see these multiple choice questions pop up, and they're usually going to be in a green box. Okay, so it's a good way for you to assess yourself and see how you're doing. Now, this first multiple choice question is simply a memorization one. And really, these multiple choice questions vary in all sorts of levels of difficulty. So give them a try. You know, if you get stuck, pause the video. If you need more time, hey, if you want to review it, go back in the video and play it again. That's the nice thing about having the lesson done like this. Right? So it's not like you have to just keep keeping up with the class. If you get stuck, you can go back and try to watch it again, try to figure it out again, pause it, do some research, whatever you need to do. All right. Which one of the following is a fundamental unit? So looking at the options, A, coulomb, B, ohm, C, volt, D, ampere. I hope you remember this from grade 9 science. You definitely would have learned electricity there. These are all units that have to do with charges and electricity, which you'll get introduced to again this year. The answer to this question relies on you having memorized the previous page. Now, I'm going to tell you right now, physics is not a science where you can memorize your way through the course. Okay? There are other subjects where this may work, but it will not work for you in physics. Now, sometimes questions that rely on memorization do come up, but the majority of problems in physics require an abstract mind, critical thinking skills, and problem-solving skills. So chances are, and I guarantee you 90% of the time, you are going to see a problem that you need to solve which you have never seen before. And this is not something strange or something odd. This is always the way it is. You're going to read through the book, you're going to gain the knowledge, you're going to understand how to use the tools used to solve different types of problems. But when it comes to an evaluation, it's not as if you're going to get a question that's from a completely different subject. It'll still be based on the topic at hand, but you will not have seen that type of question before. And you should be able to use the tools you have learned and gained, the skills you have gained to solve that problem. Okay. Some students do struggle with this in the beginning because they might be used to memorizing answers. Okay, so if you do struggle with that in the beginning, just come see me or contact me by email, send me a message through Teams, and we can try to work on some skills and strategies that can help you improve yourself. Okay, so this is just plain memorization question. The answer is D, ampere. Okay, we just saw the answer on the previous slide, so again, you would just have to remember that. And now sometimes on these slides, you're going to see references to the IB, and sometimes it's useful for you too, and sometimes it's not going to be useful to the non-IB students. Here it says the IBO, which is the IB organization, they expect you to memorize the fundamental units. And that is also expected of non-IB students, okay? So you have to memorize those 7 fundamental quantities because we're going to be using it so much. Okay. So already we've learned about what physics is, the 7 fundamental units, and now we're going to learn about those derived units I keep talking about and how to convert between units. And we're going to use something called dimensional analysis for that. All right. Now the first SI unit, the first fundamental unit that you saw was for mass. It was the kilogram. But who decided what a kilogram is? I mean, did someone just look out their window one day, look at a rock and say, you know what, that's going to be 1 kilogram. But what is that rock made out of? And over time, if dust sits on that rock or someone kicks it and a piece falls off, the mass of that rock is going to change. So how do we hold a standard mass of 1 kilogram to something that might fluctuate in mass over time, or that we don't necessarily know the mass of to begin with? Right, so in comes something called the IPK, the International Prototype of the Kilogram, sanctioned in 1889. Now, it is made of something called an alloy, so it's not just a rock found in the park. An alloy is an object that is made up of 2 or more metals. Okay, so this one is made up of mostly platinum, 90%, and 10% iridium. Now, it's formed into the shape of a cylinder, and it's held in a vault in the basement of a lab in France. Right, so this is I guess, not a blueprint, but a schematic diagram of what it looks like, and here's an actual photograph of how it looks. Now, it's a little bit hard to see, but I want you to just focus in the middle. You can see that platinum iridium cylinder inside the middle right there. And notice it's in a bell jar, and that bell jar is in a bigger bell jar, and that bell jar is in a bigger bell jar. Now, all these tubes and pipes that you see coming out of these bell jars, they are there to extract the air out of between these bell jars. So this, in between each of these bell jars, is what's called a vacuum. Now in physics, the word vacuum is not used to describe what we use to, clean up the house, clean up the floor. Vacuum means you have a region of space where there are no particles. All right, so in the room that you're sitting right now listening to this video, you are constantly breathing in oxygen and exhaling carbon dioxide. So you are filling the room with particles. And the room is already filled with oxygen in order for you to breathe. If you cough, you're putting particles into the air. This is how you know there's going to be particles in the air. If you go for a drive, you stick your hand out the window, you're going to feel that wind blowing against your hand. There are particles outside. Just because you don't see them doesn't mean they're not there. Right? Our eyes are only fine-tuned so much. With a vacuum, every single possible particle has been removed. And that means that it's a region of space that is actually, truly empty. All right? And the reason it has to be empty is so that there is no additional piece of mass that could possibly sit on that prototype of the kilogram and accidentally increase its mass. So all of these precautions go into making sure that the mass of this international prototype of the kilogram is kept constant. And there are actually copies of this all around the world, and the masses are measured every single year to see how they're changing, if they're changing, all of that. Now, what's really cool about this is that in order to get in, to actually see this prototype, you need 2 separate keys to get in, which have to be used at the same time. So it's not as if one person can get in on their own. You always need at least 2 people going in at the same time. Right now, there's actually a lot of work being done on a different type of a prototype for the kilogram that's a sphere, and I believe it's made out of silicon. I think a simple YouTube search will bring that up, but this is the original. Okay. All right, so fundamental units, we saw they were the 7 base units. Now we're going to look at derived quantities. Okay, so for example, if you have a quantity that's not mass or temperature or time or distance or any of those 7 listed on the earlier slide, how are you going to express its units? You have to still express a unit somehow. Okay, take speed, for instance. I don't know if any of you have turned 18 yet, most likely not, but many of you will turn 18 next year. You'll get your driver's licenses, you might start driving. So an important thing to watch on your car's dash is the speedometer. It tells you how fast you're going. If you're going too fast, slow down. If you're not going fast enough, speed up. All right. As you press the gas, this needle starts to move clockwise. Right now, in the car, your speed is either going to be measured in kilometers per hour if you bought your car in Canada. If the car is originally from the United States, it'll be measured in miles per hour predominantly. And most likely, most cars have both dials on them, although some of the new ones don't anymore. In physics, we do not use kilometers per hour. All right, we use meters per second when we measure speed. Now, that's not to say that a question that you're going to be given won't give you the speed of an object in kilometers per hour. And that's not to say that it won't ask you for the speed of the object in kilometers per hour. But when you take this formula booklet, so let me go back to this camera here. When you grab this formula booklet, okay, so right now we're studying 1.1. On the page where the formulas begin, there is no box 1.1, and that's because there's no formulas you're going to learn in this unit, which we're going to use in the course. It starts at box 1.2. We're not covering this again because that's going to be IB. We're going to go to 1.3. Whether it's 1.3 or 2.1, this is really where the formulas begin, this section right here. If you ever plug in a speed, which is represented by U and V, you have to plug it into these formulas in meters per second. It has to be in SI units. You cannot plug in units into these formulas that are kilometers per hour and then plug in a time that isn't an SI unit because it will not work out. Okay. So always make sure that whenever you use formulas in physics, any formula in this data booklet, please always make sure it's in SI units. All right, let's go back to the slides. All right, so speed's measured in meters per second. Acceleration, right? So when you start speeding up, if you're stopped at a red light and then the light turns green, you press the gas, this needle starts to move. It's showing that your speed is changing. When your speed changes, that means you are accelerating. How many meters per second is your speed changing? Okay, so that's what acceleration measures. Now, a common misconception is that if you're slowing down, that's not accelerating, that's decelerating. And while that is a common expression of the English language, once again, unfortunately, just like weight, it is incorrect. Now, while decelerating does mean slowing down, it is more accurate to say that if an object is slowing down, it is accelerating. And when an object is speeding up, it is accelerating. Acceleration just means speed is changing. That's it. So be careful with that. Here's the definition for the SI acronym that I showed you earlier. So SI stands for Système International It is from France, and it is the international system of units that we use worldwide. Okay, so this is so that if you have a physicist in Canada, in the US, in Germany, and Japan, when they compare their research papers, they're all able to understand one another's papers because they're in the same units. Now, they might be in a different language. Languages can be converted, but to have units also be different, this just presents a whole new layer of complexity. So the world sticks to this SI standard units. Actually, a couple years back, I used to teach physics in Miami, Florida. And so despite being in the United States where they don't use the metric system, we were using the metric system even in their physics courses. So no matter where you go around the world, it is the accepted standard of units. Now, we not only have to remember that before we use a formula, it has to be in SI units. We also have to make sure we understand what prefixes are, whether or not the formula we're using can be used, how to use something called dimensional analysis. Here's an example. Suppose the rate of a car is 36 miles per hour and it travels for 4 seconds. Let me point something out here. If you're ever given miles per hour and not kilometers per hour, you are expected to know how many meters are in a kilometer. Okay, it's 1,000. That's for sure. You need to understand that. You should know how many centimeters are in a meter, 100. How many millimeters are in a meter, 1,000. I'll show you how to remember all of those in a second. Miles, though, any other non-metric unit, you're not expected to memorize how many miles there are, for example, in a kilometer or kilometers in a mile. That's not the metric system. Right? Just for this example, just go with this for a moment. Okay? If you want, you can actually change this to kph, kilometers per hour. I think that'll be a little easier. But so when I solve this, I'll solve this as if it's kilometers per hour. It doesn't really matter what this is. But suppose that the rate of a car, also the speed, so we know the speed, we know how long it's traveling, what's the distance traveled in that time by the car. So there's a couple things you got to pay attention to here. So grab a piece of paper, or you can even solve it on your slides there. I guess in this circumstance, it would be nice to have the 2 slides where you have one big one here and then another big slide here, so you can actually fill it in. When I would do it at the school, this is how I would print it for everyone. All right. So the rate, and we're going to have a different name for this in a bit, we'll call it 36 kilometers per hour. So I just changed the miles to kilometer. And we know that the time is 4 seconds. What is the distance traveled by the car? All right. Now, how do we find distance? Well, a lot of you might be able to logically problem solve this out. Imagine instead of 4 seconds, the time was 4 hours. Okay? Imagine it was 4 hours. I'm driving at 36 kilometers per hour. How much distance have I covered after 4 hours? Well, if every hour I cover 36 kilometers, I just take 36 and I multiply it by 4. And it's 144, right? I think so, right? 36 times 2 is 72, and multiply that by 2, it's 144, right? So 144 kilometers. That would be easy, right? So what did I do? I just multiplied these two numbers together. Now, the only difference here is I'm not traveling for 4 hours, I'm traveling for 4 seconds. And the units of hours and hours don't match up. I have hours and seconds. But I do know that in order to get a distance, I have to multiply the speed or the rate by the time. So I already have an idea what the formula is going to be. Now I just have to make sure I convert my units. Now everything that I'm about to do in problem solving this is going to be explained on the slides following the current one that we're on. Okay. So 36, and we're going to write the kph like this, kilometers per hour. Okay, so that's where we're going to write that. And the time is 4 seconds. Now, you got to know a little bit of math here. All right, so if I have A over B times C, fractions are nice because a lot of the times I can cancel things out. Now, and a lot of times when I work with fractions also, I want to make sure that if I have a whole number, I understand what that whole number looks like as a fraction. So this is the same thing as A over B times C over 1. If you have just a number, you can always rewrite that as a fraction by writing it over 1. Okay, so what that means is the A gets multiplied by the C and the B gets multiplied by the 1. Okay, so you have AC over B overall. Okay, so what's the point of that? Well, the point of that is if this happened to be a B, right, instead of a C, and the B's would cancel, and I would just be left with A at the end. Right, and that's essentially what happened when I had the 4 hours. Imagine I had an H here. The H would have canceled with this H, leaving me with the K. K is kilometers. That's a unit for distance, and that's exactly what I'm looking for. So I either have to convert the hours to seconds or the seconds to hours. It really doesn't matter. So I'm going to go ahead and let's convert the hours to seconds. Now, anytime you want to convert a unit, you always multiply by 1. Okay? So to convert a unit, and I'm going to be saying this a lot during this course, I'm going to say it a lot next year, this is always the rule. You multiply by 1. Now, some of you are probably listening to that and saying, what's the point of multiplying by 1? If you multiply something by 1, you just get exactly what you started with. And you're right. But not if you pick your 1 very carefully and methodically. What is 1? Okay, 1 as a fraction. If I said 4 over 4, that's 1, right? Because the numerator equals the denominator. And right now I'm considering 1 as a fraction, okay, not as anything else, just as a fraction. If I had 16 inches over 16 inches, that's equal to 1 because the numerator is equal to the denominator. Right? Well, what if I have 12 feet, oh no, not 12 feet, sorry, 1 foot over 12 inches. Now, if I remember, no, 1 foot, yeah, 1 foot is 12 inches. I'm trying to remember Subway sandwiches here. It's been a long time, but yeah, I think 1 foot is 12 inches. The numerator and the denominator are equal to each other. 1 foot is equal to 12 inches. So therefore, that ratio is equal to 1. But notice that now I have different units on the numerator and denominator. So I can manipulate things. So I'm going to take this and multiply by 1. And I have 36 kilometers per hour times 4 seconds. And I'm going to multiply by an empty fraction. So always replace the 1 with an empty fraction. Now, whatever unit goes on top is to replace the unit you're trying to get rid of, whether it's seconds or hours. In this problem, it actually doesn't matter which one you're trying to get rid of because then you'll automatically get rid of the other one. Okay, let's say I'm trying to get rid of seconds. So since seconds is in the numerator technically of a fraction, right, because I can write it as a fraction over 1, that means I have to put seconds in the denominator here, so it cancels. I have to put hours in the numerator, so it cancels with that hours in the denominator. Now you have to figure out what ratio of hours to seconds equals 1. Generally, the unit that's bigger, which is hours, you put the number 1 in front of. Okay, so how many seconds are in 1 hour? Well, there are 60 seconds in a minute, and there are 60 minutes in an hour. Okay, so let me do this down here. This, you're not going to have to do this again the more you do this, because you'll just remember. Okay, 60 seconds for 1 minute. And 60 minutes for 1 hour. Okay, so my minutes cancel out. And so how many, well, then I'm left with 60 seconds per hour. So that's actually exactly what I want. Oh, hang on, 60 times 60. 60 times 60 is 3,600. So that's 3,600 seconds in 1 hour. All right, so what was the point of that? The point of that is now I have seconds with seconds, those cancel. I have hours and hours, those cancel. And so what is left for my calculation? I have 36 times 4 times 1. 36 times 4 times 1 divided by, and technically this is a fraction over 1. I have 1 times 3,600. Now, if we look at the units left in the numerators, k times nothing, or rather times 1, I'm left with the units of kilometers on top. And in the denominator, I have, well, 1 times 1 times 1. There's nothing left. So that means the overall units for all of this will be kilometers, which is what I want. That's a distance. That's a distance. Okay. So 36 times 4, I think we just said that was 144 divided by 3,600. Unfortunately, I can't do that in my head, so I'm going to grab my handy-dandy calculator. 144 divided by 3,600, so 0.04 kilometers. All right, the number should make sense, okay? Ask yourself, whenever you get any answer that you calculate in physics, does it make sense? And if you look back, If it takes me 1 hour to drive 36 kilometers, I'm not going to drive that far in 4 seconds. And sure enough, there it is. There's the result, 0.04 kilometers. Now, if we wanted to be really specific, we would express our answer in meters because meters is the SI unit. Right? So we would take this. Now, how many meters are in a kilometer? Well, there's 1,000 meters in 1 kilometer. So if I take this and I multiply it by 1,000, I'm going to get the number of meters. Now, in the number 1,000, you have 3 zeros. So what you would do is, since you're multiplying this by 1,000, I know that the decimal is going to move to the right, and it moves to the right the same number of spaces as there is zeros in this number. So 3 spaces, it's going to move to the right, so that's going to become 40 meters. All right, so there's our final answer. Let's go back to the slides. And so again, in the slides, it's based on miles per hour, but we're not really going to worry about miles. And on this slide, it is explained how to use well-chosen ones. Okay, so the one I wrote in quotation marks on the handwritten piece of paper. Okay, so I'm just going to go ahead and skip through these. Now, we're getting towards the end of today's section, so I'm just going to finish it off by going through a couple things here. Determining whether an equation is consistent or inconsistent. Consistent means the equation might work, and inconsistent means the equation is false, guaranteed false. Okay, so again, consistent, it might be correct, and inconsistent, it is incorrect. All right. Now, you essentially saw before, well, actually, let me go back to the page here for a moment so you can see. In this problem, we saw that distance is equal to rate times time. Now, that rate was essentially a speed. So effectively, you've seen this formula. Distance is equal to speed times time. And in fact, we're not going to actually be using d for distance. We're going to be changing that to an s, but just for the sake of introduction, imagine it was distance equals speed times time with a d. Okay? That formula we know to be true. Now, going back to the slides, what about d is equal to 8 times t? Distance is equal to acceleration times time. Is that correct, and does it work? Well, since you actually saw the formula before, many of you are probably already guessing correctly that that formula is not going to work. But how can we prove that? Like, how do we know for sure that that formula doesn't work? Well, you have to do something called dimensional analysis. You have to look at the units on the left side of the formula, look at the units on the right side of the formula, of course with appropriate simplifications where necessary, and see if they match. If the units don't match, that means the equation is inconsistent and it is false. If the units do match, it might be a correct equation, but not guaranteed. Okay, so instead of going through it on the slides, I'm going to show you by writing it down. So let's go to another sheet here. Okay. So right now we're trying to compare distance is equal to acceleration times time. So again, we're doing unit analysis. When I do unit analysis, I like to use square brackets to represent the units. Okay, so on the left side, distance is measured in meters. This is the SI unit. Now, for the right side, acceleration times time, right? Acceleration is measured in meters per second squared, and time is measured in seconds. So you're multiplying a fraction by a non-fraction. But remember, when something's not written as a fraction, you can rewrite it as a fraction. So this is meters per second squared times seconds over 1. Now I have seconds in the numerator of the second term of the product and seconds in the denominator of the term in the first term of the product. So I can cancel 1 second out in the top with 1 of the seconds in the bottom. Okay, so what am I left with? I'm left with meters per second. That is a unit for speed. And on the left, I have a unit for distance. So I can see that left side does not equal right side. Therefore, equation is inconsistent. And we're going to be doing a few more examples of this. Let's go back to the slides. So everything we just showed on the page, it's here on the slides as well. Excuse me. All right, so here's another example. So we're going to decide if these formulas are consistent, if they're dimensionally consistent. Okay, so we're going to do what we just did for A, B, and C. Okay, so the information we need to know is that V is measured in meters per second, A is in meters per second squared, X is in meters, and T is in seconds. Okay, so just pause the video for a second, write these down on a piece of paper, and give it a try yourself. Okay, then if you're really getting stuck, you can play the video and see how I'm solving it, or if you're finished and you just want to check your answers, of course, play the video and see how you did. But pause the video right now and see if you can solve these on your own first. Okay, hopefully you had a chance to go and pause the video, solve these on your own. Okay, we're going to go to the sheet of paper here, and I'm going to solve each one of these. So this is the example or the practice. So for part A, we're trying to see if V is equal to A times T squared is dimensionally consistent. So we're going to look at the right side here, and we're going to, or sorry, left side and also right side. The left side is going to be the short one. So V is speed. We're told in the question that it's measured in meters per second. The right side is acceleration times time squared. Acceleration is meters per second squared. And the second unit for time, it's getting squared, right? So I have to remember to put that there. Time is measured in seconds. Now, just like before, I'm going to rewrite seconds as a fraction. So this is meters per second squared times seconds over 1 squared. Now, getting this next part is going to require that you remember exponent rules. Okay, if you have, let me write this in a different color. Let me write it here. If you have a fraction, oh, and this pen doesn't work. Hang on 1 second, please. Okay, if you have a fraction, A over B, and you raise this to the power M. Okay, so how do you deal with that? Well, you take that M and you apply it to the numerator and you apply it to the denominator. And it becomes the exponent for both of them. The reason for that is because it's outside the bracket. So this becomes A to the M over B to the M. Okay, so make sure you remember that exponent rules are very important in physics. Okay, so that means the 2 gets applied to the S and to the 1. 1 squared is just 1. So M over S squared times S squared over 1. So now I have S squared in the denominator, S squared in the numerator. Those cancel, and I'm left with meters. Meters is not the same as meters per second. So left side does not equal right side. Therefore, equation is inconsistent. Now, if you didn't try these ahead of time because you wanted to see me solve another one, I really strongly encourage you to pause the video here before we move on to part B and solve it. So give it a try before you see it. This is the best way for you to learn, by trying it yourself. Okay, so hopefully you gave the video a pause there. I'm going to go ahead on to part B now. V squared is equal to 3ax. Okay. So left side, I have V squared, right? So that's whatever the symbol for V is, the unit for V is, squared. V is speed, that's measured in meters per second. And on the right side, I have 3ax. Now, the 3, it's just a number. It's a constant multiplier. It doesn't have units associated with it. And actually, that's the major reason why, just because you find out that an equation's units do match, let's say, that doesn't mean that it's the right equation, because you don't know if the number that's in front is the correct number. If you don't see a number in front, that means it's invisibly a 1. And if there's a fraction there, or a negative number, or a non-zero integer, positive integer like 3, you don't necessarily know if it's correct. And that's why you cannot know for sure if the equation is correct. Okay, well, let's see what happens with this case. Okay, so I'm going to ignore the 3. Acceleration unit times unit for x. Okay, acceleration is meters per second squared, and x is measured in meters. Okay. So I'm going to rewrite the meters as a fraction. That's going to be meters over 1 So that becomes meters squared per second squared. Now, based on the rule of exponents that I just showed you, if you have exponent like a fraction raised to an exponent outside the bracket, you can take that exponent and you apply it to each piece inside, giving you a to the m over b to the m. And that's essentially what we have here in this example. In the left side, we have m over s all squared, and on the right, we have m squared over s squared. Okay, so these two are actually the same, but don't leave it like this. Show it actually looking the same. So I can rewrite this as m over s squared. That's when I stop. Okay, so left side equals right side. Therefore, equation is consistent. Now, this is what I mean. You see this equation has a 3 in front. If there was a -6 in front there, it would still match. The left side would still match the right side, and we would still get the result that the equation is consistent. That's why we can't say that just because it's consistent, it's true, right? The number in front can just change. And part C, x is equal to a times t squared. So on the left side, x is a distance. We measure that in meters. And on the right side, we have acceleration times time squared. So acceleration is meters per second squared, and time is seconds, and that's getting squared. Okay, so we have meters per second squared. Rewrite the s over 1. Okay, again, exponent rules, the 2 gets applied to the s and to the 1. 1 squared is 1, so that's not that interesting. We have m over s squared times s squared over 1. So the s squareds cancel, and I'm left with m. So once again, the left side does equal the right side. Therefore, equation is consistent. Again, consistent, but not necessarily the right one. And in fact, we're going to see why on the slide right now. So let's go back to the slides. So the solutions we've already done. We've used dimensional analysis to prove. If you look at the bottom of this red box on the slide, it says the actual equations should be 2ax, that's for B, not 3ax, it should be 2ax. And for C, it should be 1/2 at squared instead of 1 at squared. And I don't want you to go ahead and memorize these equations because even these are not the full equations. These two are equations that you get when you simplify the original equations based on something called the question's conditions or the boundary conditions. Okay, so these equations have already been simplified, so don't memorize these, okay? When we get to equations, we'll get to them. Right, and I believe scientific notation, nope, sorry, this, we have just a couple more things to cover and then we're going to stop. Metric multipliers and scientific notation, and then scientific notation will be the last thing we cover. All right, prefixes. Well, I'm sure you've heard of the prefix kilo, giga, mega, tera, especially if you know anything about computers or even if you've bought a hard drive. So back when I was growing up, and I know you're all going to laugh at this and I'm really showing my age here, but when I was growing up, the fast internet speed was 32.2 kilobytes per second. And while many of you are thinking that it would probably take you 3 whole days to load your web page at 32.2 kilobytes per second, you got to remember that back in the day, and I speak very loosely here when I say back in the day, the web pages weren't full of so much information. So they actually didn't take that long to load. It took almost as long as they do nowadays. But nowadays, the web pages are a little bit more complex. Well, maybe not a little bit more, a lot more complex. So let me go ahead and post these all here on the slide. Okay, so kilobyte, again, that's pretty slow. Megabyte, most likely your internet speed's in the megabytes right now. I doubt it's in the gigabytes. If it is, that's pretty nice. Terabyte, maybe you bought a hard drive recently, external hard drive. Most likely it's measured in the terabytes. But you know, you should even recognize the prefix kilo based on measuring units. Hey, if you go on the highway or you just go with a friend or you grab an Uber or you go with your parents, on the highway everything's measured in kilometers. Go kilo and then meter. Right? We just pronounce it kilometer. 10 to the 3. So this number actually represents 1,000. Okay, so a kilometer is 1,000 meters. 10 to the 6, this represents 1 million. So a megameter is 1 million meters. A gigameter would be 1 billion meters, okay, etc. Oh, actually, while we're on this slide, let me just show you one quick thing. If you go to your formula booklets, and I'll be doing this a lot throughout these slides. 1.1, it doesn't happen as much, but we will see this more and more throughout the other lessons. In your formula booklets, on page 2, so the bottom right, it has page numbers, so on page 2, you're going to see metric SI multipliers. So they're all listed here. In fact, there are more listed here than there were on that slide. I think there's 2 more. This one goes from minus 10 to the 15 to 10 to the 15. So there's those 2 additional ones. So you've got the abbreviation, the value, and what they're called. In case you ever forget, it's there for you to look up. Okay. Scientific notation. Now, earlier in the slides, we saw that physics is responsible for measuring things that are very big and things that are very small. And things that are very big and very small have very difficult units to deal with. And so we need a way of expressing them that ensures that we don't write numbers that take the whole page to write down. Okay, so numbers expressed in scientific notation generally have this format right here, a times 10 to the b. So there's a number in front, a, this is called the coefficient, and this number is usually between 1 and 10, although it can't equal 10. Okay, so anything under 10, like 9.999, it can be as high as that. And b, the exponent on the 10, that is an integer. So it's a positive, negative number, 0, but it can't have decimals after it. Okay, and here it is. The absolute value of the first number is between 1 and 10, but not equal to 10. Best way is to learn by example. Now, again, the idea behind scientific notation is to write things like this huge number in seconds and this really small number in seconds into a more manageable form, and so that it's also easier to read, as we'll see. But you can write any number in scientific notation. Take 2 seconds, for example. Okay, I know the form has to be some integer times 10 to the exponent. Okay, so the integer is going to be between 1 and 10, not equal to 10. So I'm going to just pick 2. So 2 goes in front. Now, I have to multiply this by 10 to some number that I only get 2 back. And the only way to do that is to multiply it by 10 to the 0. In mathematics, if you take any number and you raise it to the power 0, it automatically becomes 1. Okay? Any number raised to the power 0, 10 to the 0, in brackets, -5 raised to the 0, 239 to the 0, 10 to the 0. It's equal to 1. So this right piece here, that's 1. So 2 times 1 is 2. And so we have 2 seconds. 300 seconds. So what number do I pick out of this? Well, I'm not going to pick out 300 because that's not between 1 and 10. 30 is not between 1 and 10, so I pick out 3. So the 3 goes here. Now, how do I make that 3 into 300? Well, I have to multiply 3 by 100. Okay? And 100 I can represent as 10 to the 2. Another way to look at this is you look at the decimal that's here, the 2, and this tells you how many spaces to the right or to the left you have to move the decimal, which is in the front here for the coefficient. So the coefficient decimal is right here. If you can see my mouse, it's right there on the bottom right of the 3. Okay, so because the exponent on the 10 is positive, that would mean that I move my decimal to the right. If the exponent is negative, that means I move the decimal to the left, a certain number of spaces. Because it's positive 2, that means I move the decimal to the right 2 spaces. So 1, 2, that means I could fit 2 zeros there, making 300. All right. Okay, now this next number is interesting. Writing something in scientific notation does not always guarantee that it's going to look much more simplified. Sometimes it's going to look a lot more complicated. And sometimes it's not worth it to write it in scientific notation, although sometimes you just have to do it. This is one of those examples and cases. 4,321.768 seconds. All right, so the number I'm going to pick is going to be 4, but I don't just want to pick 4. And the reason for that is if I just put 4 here times 10 to the 3, I'm going to lose all of this precision in the number, all of this accuracy. However this information was collected, I don't want to lose that information. So I keep all of the rest of the trailing numbers as decimals. So 4.321768. Now, how do I know that the exponent has to be 3? Because when I have this original number, and again, it's between 1 and 10, not equal to 10, if I have this decimal, how many places do I have to move it and in which direction to get it to look like this number? Well, right now the decimal is 3 spaces to the left of where it would be here. So I have to move it 3 spaces to the right. 1, 2, 3. I got to stick it right here between the 1 and the 7. Since I have to move it 3 spaces, I have to put a 3, and since it's to the right, it's a positive 3. All right, so that is why these two numbers are the same. Now, scientific notation you can use for positive numbers, negative numbers, decimals, simple numbers. Okay, so the next one is with the negative number. Again, the closest number between 1 and 10. Again, the number in the front has an absolute value between 1 and 10. So you can have negative 5.3, that's fine. You just can't have negative 53 or positive 53 because that would be outside the realm of absolute value of A is between 1 and 10. So negative 1.3, and then what do you do with this decimal? You would have to move it to the right 4 spaces to make it look like this number. Finally, we arrive at an example that was probably a bit useful to us. Okay, so we here have, let's see, so this would be 6,720,000,000 seconds. That's a really large number. Okay, so instead of writing it like that, we can write it like this. So extract the number out with some appropriate decimal places. So 6.72. You don't need to include the trailing zeros because those are really going to be just placeholders. I mean, you don't have to stick them in the decimal here. Those of you studying significant figures, you might learn that it sometimes becomes important to stick the zeros there, but for our purposes, you don't need to do that. So 6.72. Now, if I put the decimal here, how many places do I have to move it and in what direction to get this number? Well, for sure, I have to move the decimal to the right because the number has to be bigger than 6.72. It is, after all, 6.72 billion. So I have to move it to the right, but how many spaces? Well, right now the decimal would be here, technically. I have to move it 3, 6, 9 spots. So there's the 9 right there. Now, what's nice about this example is that, and I'll come back to this part in a sec, the 10 to the 9, if you go to your data booklet, so I actually shouldn't have closed it, let me just grab it again. If you look at your metric multipliers, 10 to the, where is it? 10 to the 9 is giga. Oh, let me see if I can get that to focus. It usually has a hard time focusing here, but 10 to the 9, okay, I won't try to hold this up too much, but it's the third one down from the top. 10 to the 9, abbreviation capital G, that's giga. So instead of saying 6.72 times 10 to the 9 seconds, I can say 6.72 gigaseconds, okay? The previous one, 10 to the 3, that's another famous one. 10 to the 3 is kilo. So I can say 4.321768 kiloseconds. The last one down here, this is an incredibly weird small number. And I mean, how would you even read this? Instead of having to say 0.00000000751 seconds, that's a mouthful. It's so much easier just to say 7.51 nanoseconds because 10 to the negative 9 is nano. Right? So if you were to have 7.51, sorry, that would mean the decimal would be right here. And to get to where it is supposed to be, I have to move to the left 3, 6, 9 spaces. Since I'm moving to the left, the exponent is negative, and I'm moving 9 spaces, hence the 9. All right. Now, you can take any of these numbers and express them in terms of the abbreviations. The abbreviations on the page are all based on orders of 3 for the most part, except towards the middle. Like, for example, 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12, 10 to the 15. But you can even express things like 10 to the 2 or 10 to the 4 in terms of these prefixes as well. So for example, we can call this one here minus 53 kiloseconds. Okay, so why is that? If you have minus 53, that means your decimal would be actually right here, right? So right now what we're being told is that this decimal has to move to the right 4 spaces in order to become the number it's supposed to be, which is this, minus 53,000. But imagine you stick the decimal here. You're not technically supposed to because that number in front should have an absolute value between 1 and 10. But let's say you did. If you did stick that decimal right there, well, you've already accounted for the decimal moving to the right 1 space. So it only needs to move another 3 spaces, not 4. Okay, so you would have minus 53 times 10 to the 3, and 10 to the 3 is kilo. So minus 53 kiloseconds. Now, of course, you wouldn't represent the scientific notation like that, but you can write the number like this in the end. Okay, likewise, this one down here, and I do know that I've skipped this one. I've skipped it on purpose, so you can try to work this one out yourself. We can also write it as 200 milliseconds. Okay, so that is the end of this video. We're not going to be covering the rest of 1.1 because it's not going to be covering stuff that we need for our course. So 1.1 measurements and physics is done. Read teams to see which pages in the textbook you need to pay attention to, which worked examples you need to try, and which questions in the homework are going to be necessary for practice. All right, so that's it for today, for this video anyways. Stay tuned for the next video.